Welcome back, everyone, and we are continuing with our study of double displacement reactions. And we're on page 9 of the Chapter 6 lecture note outline. And we're going to finish up double displacement today. And we've looked last time at what a double displacement reaction is, and then we learned about the type of double displacement that produces a precipitate. Now, double displacement reactions don't always produce a precipitate when they occur. There are two other types of double displacement reactions that we are going to learn about. And the first one of those, which we're about to talk about, is the type of double displacement reaction that is known as an acid-base neutralization reaction. Now, a double displacement acid-base neutralization reaction is a type of double displacement where we are reacting something that we're going to call an acid and something that is called a base. Now, you've probably heard about acids and bases before, I'm sure, but we're going to start learning more about the chemistry, the specific chemistry of acids or bases. And while we're going to have a full chapter on acids and bases, we want to be able to learn a little bit about them now. So I'm going to simplify the concept of an acid and a base for now so that we can just get to use these concepts. And I'm going to tell you about what we're going to think about what an acid is or what a base is. And one thing to keep in mind for double displacement reactions is that when we are doing an acid-base reaction, what the driving force for these acid-base reactions is the formation of, when we mix an acid and a base, the formation of a molecular compound. So when we did a precipitation, the driving force was the formation of a solid. The driving force in a acid-base neutralization is that we form either water as a molecular compound or something like acetic acid, which is also a molecular compound. So keep that in mind. And remember, a molecular compound is one that involves all nonmetals. There are no metals in the formula. So let's talk about what an acid or a base is so that we can look at these double displacement acid-base neutralization reactions and be able to speak about them and describe the different reactants in terms of what we expect them to do. So in a double displacement reaction, we are going to look for an acid, and you're going to have to identify where the acid is. Now, we're going to talk about acids as chemical compounds where we see hydrogen with a positive charge is the first thing in the formula. So you look at a formula and you see H written first, and if it is with another ion next to it, it could be a mono or a polyatomic ion, we want to consider that as being an acid. So H plus is the first part of a formula. So here are some examples. The first one here, which is HCl, is called hydrochloric acid, and we see H plus is right next to Cl minus, and that's what makes HCl an acid. We also have nitric acid, where H is before nitrate, sulfuric acid, where H is before sulfate, and phosphoric acid, where H is before phosphate. Now, some of these acids have one hydrogen, or what we're going to call a proton later on, which is an H with a plus charge. These are called monoprotic acids. Now, we also have acids where there are two of these hydrogen plus ions. Like for instance, with sulfuric acid, we have H2SO4. This is called a diprotic acid because it has two of these H plus ions. And then we also have triprotic acids like phosphoric acid written here. This has three H plus ions with phosphate. Now, just a quick note. We're using this word protic here, monoprotic or diprotic or triprotic. And what do I mean by protic? Well, the word protic is a sort of derivation of the word proton. And you might remember a proton is a subatomic particle that is in the nucleus of an atom. And it has a positive charge, a +1 charge for every proton. Now, a hydrogen atom that is neutral, I'm going to write this down here below. A hydrogen that is neutral, just a hydrogen atom, has one proton and one electron, right? Because the proton has a +1 charge and the electron has a -1 charge. Now, if you have an H atom, but it is not neutral, meaning it has a plus charge, what subatomic particles are present on that H plus ion? Well, it lost its electron, so that means it only has one proton left. So that is why we call an H plus ion a proton. And that is why we use the word protic to describe acids that have one of these protons on them, or an H plus ion. So with HCl, we have a monoprotic acid because there's one hydrogen that has a plus charge, and that is essentially a proton. So monoprotic for these two, diprotic for this one, and triprotic for this one. So that's where that word proton comes from. Now let's look at the makeup of these acids, the monoprotic and the diprotic acids. Why is there only one proton on hydrochloric acid? Well, that's because chlorine, or chloride I should say, has a -1 charge, so we only need one proton for it. With sulfate, we have a 2- charge, so it needs 2 protons to balance its charge. And for phosphoric acid, we have 3 protons to balance the 3 negative charges on phosphoric acid. So that's what acids are. Let's also talk about bases. We're going to keep it simple for bases right now. We're going to say that a base is any salt that contains the hydroxide anion. Okay, so now that we have sort of a simple working definition for something that we're going to call an acid and something that we call a base, we're now going to talk about the reactions between acids and bases. And we're going to think about these in terms of being double displacement reactions. So we're going to have an acid and a base as a reactant together. So we're going to have an acid, and then we're going to combine it with a base, and we're going to see what reaction takes place. So if we have an acid and a base in an acid-base reaction, the products for these many of the time is simply water and a salt. So if we take an acid and we react it with a base, very frequently the products are just water and a salt. This is true for many acid-base reactions that we see. Now, it's not true for all of them, but we can use this to help us understand some of these simple acid-base reactions. Let's look at this example below. Now, we are going to look at this just like we normally would look at any other double displacement reaction. So the first thing we're going to do is we're going to identify what are the cations that are present in the formulas. Because remember, in a double displacement reaction, we are exchanging the cations. So cation on the acid will go to where the cation is on the base. So I have an arrow here drawn to the cation in the acid, which is HCl. Now let's look at the cation also in sodium hydroxide. Well, the cation would be sodium there. And remember, we're doing a double displacement, so those two things that I've put in squares there, we are just going to exchange those to come up with the symbols for the products. Okay, so let's try to do that. So the cation in HCl is H+, and the cation in sodium hydroxide is Na+, or sodium cation. And these two cations are going to exchange positions. So the symbols for the products will be sodium with chloride, or NaCl, and then we will have hydrogen, the H+, with the OH-, which is hydroxide. So let's do now the charge balancing step. Sodium has a +1 charge, and chloride has a -1 charge, so we only need one of each. And then H+ has a +1 charge, and hydroxide has a -1 charge, so we only need one of each. Now, I'm just showing the charges balancing out to 0 here. And of course, HOH is just water. We usually write that out as H2O. Now notice the products that I have in this acid-base reaction. We have water and a salt, just like I showed up above. So this is a good example of a typical acid-base double displacement reaction. We have an acid, HCl, and a base, sodium hydroxide, and then we form water and a salt. Now remember the 4-step procedure that we go through whenever we're doing a double displacement reaction. We've done all those 4 steps here, just a little bit quick. We're going to go through them systematically in the next examples, but I just kind of went through this quick to show you what these look like. So the first thing that we did is we figured out the symbols for the products. So I exchanged the cations, sodium and hydrogen, and then I put the right anion with each of those cations. So the first step is we wrote the symbols out. Then the next step is I charge balanced those. So I made sure we had the right subscripts on each of the cations and anions. So in this case, we didn't need to do any changes on them because everything worked out as charge balanced already. Now, the next step would be to put in the phases for each of these. So we have to figure out, what is this? Is this aqueous or a solid or a liquid? And then water, is it aqueous, a solid, a liquid, or a gas? And that's what we're going to do right now. So we look up in the solubilities table and we find that sodium chloride is soluble in water, so we put an AQ next to it. And then water, of course, is a liquid, and it's, of course, a liquid that's soluble in itself, so it's just L for that. What we would normally do here is rewrite HOH as H2O. Let's go to the next example and try another one of these. So the first thing we do is identify what are the cations in our double displacement reaction, because those cations are going to exchange in our product. It also might be helpful to identify which one of these is the acid and which one is the base. So I'm going to put little arrows to the acid and the base. Right? Acids are hydrogen first, and bases have hydroxide in them, salt with hydroxide. So here we have sulfuric acid and sodium hydroxide, and we're going to write the symbols out for the double displacement. Let's make a little checklist at the bottom here so that we follow this sort of 4-step process for writing out the correct products for this. So we're going to write the symbols, then we're going to fix the subscripts. I also call this charge balancing. And then after we fix the subscripts, we are then going to go and assign the phases, so aqueous, solid, liquid, gas, that sort of thing. So the states of matter. We would use the solubilities table to help us do that. And then finally, we're going to mass balance the whole thing, right? And that's making sure that the coefficients are correct to give us the same masses for all of the different elements. So let's do step 1. Let's write the symbols out. So we're going to have sodium, and sodium is going to be with sulfate because of the double displacement. And then we're going to have hydrogen, and hydrogen will be with hydroxide because of the double displacement. Let's put a little space for our phases, and we're done with the first step. Now let's move on to the subscripts. So for this, we need to make sure we know all the charges. Sodium has a +1 charge. It's a group 1A metal. Sulfate has a 2 negative charge. So if we want to get a neutral compound out of these two things, we recognize there are 2 negative charges on sulfate, but sodium only has a +1 charge. That means we need to have 2 sodium atoms in order to get the 2+ charge. So we have 2 sodium atoms, and that means we need to have a 2 subscript on sodium sulfate. Let's do the same analysis on HOH, or water. Hydrogen has a +1 charge, and hydroxide has a -1 charge. To get a neutral compound out of this, we just need one of each, right? +1 and -1 goes to 0. So we don't need to change the subscripts on this. It's good. So we form water, and we also, that's our water molecule. We might want to change that to H2O. So I'm going to actually erase this and just rewrite it as H2O. And that's our subscript step. So now we're going to do the phases. Now we're going to look at the solubility chart that's on Canvas. You can print that out. And we look at sulfate, and we find that sodium is soluble in water, and we know water is a liquid. Now I'm just going to erase a few of my notes over here so that we can see everything as we do the mass balancing. Now it might be a little confusing as to why this 2 coefficient is already in front of our sodium hydroxide. The reason for that is it has to do with the product side. So if you notice on the product side, we have the formula sodium sulfate. And sodium sulfate has 2 sodium cations in it. And that's a subscript 2 there. So in order to allow for sodium to be balanced on both sides, there has to be a 2 coefficient in front of the sodium hydroxide, right? We can't put a subscript on the sodium because that wouldn't be the formula of sodium hydroxide. It has to be a coefficient. So that's why that 2 is already there. Now let's look at the rest of the balancing that's going on this. So we have to look at all of the atoms. So we have to look at hydroxide, sulfate, and hydrogen. Now remember, there was a trick I showed you previously, that is the number of hydroxides on one side, meaning there are two hydroxides here, should be equal to the number of water molecules on the other. And if it isn't, that means you probably want to rebalance that. So if we see two hydroxides here, that means there probably should be two waters on this side. So let's write that out. We've got two hydroxides on the reactant side. That means we need two waters on the product side. Our sodiums are already balanced. Let's move on to sulfate. There's one sulfate on the left, and there's one sulfate on the right. Now, if you want to double check the water and the hydrogen atoms, you see that you have two H+ ions and two hydroxide ions. And that means you would need two waters. And that's why the water hydroxide trick works. Where do those two hydrogen atoms come from? Well, they come from the acid, which is diprotic. So the diprotic acid provides the two protons that react with the two hydroxide ions to make the two waters. And that's why all of this balances out. So that water hydroxide trick is really nice for that reason. So let's review what we did. We wrote out the symbols first, right? We got our sodium with sulfate and our hydrogen with hydroxide. Then we fixed our subscripts, meaning we did the charge balancing. That's where we had this subscript 2 next to the sodium because we needed two sodium atoms to balance out with our sulfate. The next step is we got the phases and the states in. We used our solubilities chart to help us figure out that sodium sulfate is aqueous. And then we did the mass balancing, which made us fix this 2 coefficient in front of water. And this would be the complete finished equation. We have one molecule of sulfuric acid reacting with two salt ions of sodium hydroxide to give us sodium sulfate and two water molecules. So let's go to the next page and do a few more examples. So another type of double displacement example that we will look at are double displacement reactions that result in the formation of a gas. Okay, so we've seen solids, we've seen liquids or acid-base reactions, and now we're going to look at gases being formed. Now, in order for us to do this well, we need to be aware of what are some of the common gases. That way, if we see one of these as a product, we know that it's a gas, and we know to put the letter G in the parentheses next to it. So I'm going to write out for you some of the most common gases that we will see. And then we're going to look at some examples of double displacements that will produce these gases. Now, there's a few other things that we'll have to talk about when we do this. Namely, there are some products that we will form in double displacement reactions, namely carbonic acid and sulfonic acid and ammonium hydroxide. These three things, when we see them, we're going to have to remember that those decompose to these gases. So we'll look at that as well. Let's first start off, though, by looking at what are the common gases. So some of these gases you'll be really familiar with, like carbon dioxide. That's one of the most common gases that we see in this class. Another really common one, though, is ammonia, which is NH3. That's also a gas. We also get hydrogen sulfide, which is H2S. That one smells like rotten eggs. And then we get cyanide gas, toxic, HCN. Then we get sulfur dioxide. And that's also one that smells kind of like burning rubber. So those are the most common gases we see. There's 5 of them. You definitely want to remember when you see those that those formulas would result in the gas phase. Now let's look at this first example reaction that I have here below. So we have 2 reactants. We've got our nitric acid. Notice there's already a 3 coefficient there. We're going to see why that is here in a bit. But anyway, we have nitric acid and we have iron cyanide. Now this is another double displacement reaction. We see we have an aqueous, kind of like a salt, but it's an acid. And then we have an aqueous salt. So we have an aqueous acid and an aqueous salt. And this is undergoing a double displacement. The first thing we want to do whenever we're looking at these is identify the cation on each of the reacting partners. So we see the cation here I've drawn in the square is hydrogen, and then we have the other cation here, which is iron. And we're going to write the symbols in the first step, the symbols for the products, just by moving, doing the exchange of these cations. So this hydrogen, this proton, will be where iron is in the product. So it will be with cyanide rather than iron with cyanide. The other product will have iron, but that will be with nitrate. So it will go over here. So let's see how that works. Okay, so let's start writing the symbols out. We're going to have hydrogen with cyanide, and we're going to have iron with nitrate. Now notice as I'm doing this that I'm not bringing over any subscripts that don't belong on the polyatomic ion. So for example, we know that nitrate, the formula for nitrate, includes the subscript 3. So the nitrate is an NO3. So that's why I bring over the entire formula NO3. Notice that is over here. Now, cyanide, on the other hand, which is the formula CN, the formula for cyanide does not include the subscript 3. This is telling us there are 3 cyanides here. That's irrelevant to what I'm drawing on the product side. On the product side, I just want the formula for the polyatomic ion. I'm not carrying over the 3. Okay, we're going to figure out what the subscripts are on these things here in the next step. The first step is I just want to write down the right symbols. So I carry over the monoatomic and polyatomic ions as their formulas would suggest. So let's now move on to the next step. After we write the formulas, we want to figure out the subscripts, and we do that by charge balancing. Okay, so we have hydrogen, which is +1, and we have cyanide, which is -1. So when we're thinking about the charge balancing, we have one cation with +1 charge, and we have one anion with a -1 charge. So these already neutralize as they're written, so we don't need to do any adjustment on their subscripts. Now let's look at iron and nitrate. Iron is a variably charged metal. Nitrate is -1. To figure out iron, we need to look at the reactant side. So we see iron on the reactant side has 3 cyanide ions with it. Each one of those cyanide ions has a -1 charge, giving us a total of -3. Now for this to be a neutral compound, that means we must have the corresponding cation charge, which must also be +3. That's because everything has to add up to 0. So what is the charge on that iron atom? That's right, it is 3+. And the charge is not going to change from reactant side to product side. So our iron is 3+, and our nitrate is -1. So how many nitrates do we need? Well, to get a -3 anion, we need to have 3 of those nitrates, right? Because we have to have -3 to balance out with a +3. So we have 3 nitrates, and we need to fix this formula by putting parentheses around nitrate with a subscript 3. Okay, so now we can move on to the next stage, which is writing the phases. Hydrogen cyanide is one of our common gases, so we write G, and iron nitrate is aqueous. We can find that out by looking at the solubility table. Now, what's the last step that we need to do? We've done our symbols, we've done our subscripts, and we've done our phases. The last step is to verify that all of the coefficients are correct, to do mass balancing. So let's take a look at what we've got here. Notice that the metals, iron and iron, are already balanced. So that's a nice place to look first to see if you need to balance metals. Notice, however, there are 3 nitrates in iron nitrate. That means we need to make sure that there are 3 nitrates on the reactant side as well. So let's go and look at those. Well, here we go. Notice that there's already a coefficient 3 in front of this nitric acid, meaning there are 3 nitrates to balance with our 3 nitrates with iron nitrate. So these nitrates are already balanced. All right, so let's see if there's anything else we need to worry about. Well, notice here that iron cyanide has 3 cyanide groups, 3 cyanide ions with it because of that subscript 3. But notice over here with hydrogen cyanide, or a cyanide gas, we only have 1. So we need to fix that. To make this balance, we need to make sure there are 3 CNs. So we have to put a 3 coefficient right in front of HCN. And that gives us a balanced CN. That also means that we have the 3 hydrogen atoms that are resulting from this 3 coefficient in front of nitric acid. So H is balanced as well by putting that 3 there. So now if we check everything, we see the hydrogen is balanced, the nitrate is balanced, the iron is balanced, and the cyanide is balanced. So it's completely balanced. So we're done. Let's go to the next example and try another one. All right, so we have another double displacement here. What I want you to do is pause the video and go through the same 4 steps that I've been showing you and see if you can get to the same result. And then when you unpause the video, you can kind of follow along with my solution and see how you did with it and maybe clear up any points of confusion you have. So follow that 4-step procedure. First, look at the reactants, find the cations, write the symbols out where you exchange the cations between the 2 reactants on the products, and then do charge balancing. So make sure the subscripts are all correct. After you do charge balancing, get the phases in there correctly. So figure out if there's a gas or if something is a liquid or a solid or aqueous. You can use the solubilities table if you need to do that, or the list of common gases above. And then finally do the mass balancing. So fix the coefficients, make sure everything is balanced out. So go give that a shot, and then when you unpause the video, I will show you and explain my solution. Okay, so the first thing we're going to do is do the exchange of the cations. So we find the cation is hydrogen and sodium on both of the reactants. So let's put hydrogen with sulfur and put sodium with chloride. Now let's do charge balancing to make sure that we have the correct subscripts on each of our formulas. So hydrogen is +1 and sulfur is 2 negative. To get this to be a charge balanced compound, we need 2 protons to give us the 2+ charge. That will balance with our 2 negative charges on sulfur, so we need a 2 subscript next to hydrogen there. Let's do the same process on sodium chloride. Sodium is +1, chloride is -1, so this is already a charge balanced compound. Now we can do the phases. We have hydrogen sulfide as a gas, and sodium chloride is aqueous. Now mass balancing. We have 2 sodium atoms on the left, so we need a 2 coefficient on the right to make that match. And then we have 2 in front of the HCl there. That gives us 2 hydrogen atoms and 2 chloride atoms to balance with the 2 on the right in the case of hydrogen sulfide and sodium chloride. So everything balances as it's written, where we have 2 in front of HCl, 1 in front of sodium sulfide, and then a 1 in front of hydrogen sulfide gas, and a 2 in front of sodium chloride. So that is this example. We've done all of these steps. Let's go to the next one. Now, this example below has a little bit of a trick inside of it. So we're going to get a chance to learn a little something on this one. So I want you to try it first. I'll pause the video and go through at least the first couple of steps until you get stuck, and then we'll talk about what happens next. So what you're going to do first is identify the cations, which we see here are the cations are hydrogen in HCl and sodium in this sodium bicarbonate formula. So I'm just going to underline the cations in each of these, and then let's write the formulas out. So we're going to have sodium with chloride, and then we're going to have hydrogen with this HCO3. So the formula becomes H sub 2 CO3. And this is where the little trick comes in. This molecule, which is called carbonic acid, is an unstable compound. It actually decomposes pretty much the instant that it is formed. And what it does is, so it's aqueous at first, but what it does is it decomposes into a gas. So let's go look up above in the notes real quick and see what I'm talking about. Notice here we have these 3 reactions, and one of them is this carbonic acid. And notice it decomposes into water and carbon dioxide. So that's what we're going to actually do. We're not going to have this carbonic acid there because it's unstable. It decomposes into a gas. So I'm going to erase it. You can cross it out or erase it. And I'm going to replace it with what it turns into, which is water and CO2. So let's write out all of those elements, water and CO2. And you'll notice actually, if you look at the formula of water and CO2 and you put it together, it equals H2CO3. These are the actual products for this double displacement reaction. So I'm going to make a little note here that H2CO3 decomposes into H2O and CO2. Now, we just have a few other housekeeping items to do on this reaction. So let's put in the liquid for water, and let's verify all the elements are balanced. So we have one sodium on the left. So we see the sodium there, and we have one on the right. We have a hydrogen over here and a hydrogen over here, so there are two hydrogens, and then we have two hydrogens here. We have a chloride on the left and a chloride on the right, and we have a carbon and a carbon, and then we have three oxygen atoms over here, and if we add up all the oxygen here, it's also equal to 3. So everything is balanced. Now this decomposes to a gas phenomenon, happens with a few other molecules as well. So I just want to go back up to that part in the notes and look at it real quick. So let's scroll up here, or you can look on yours, and notice here there are a few reactions where this happens. So we just looked at the one where we have H2CO3, or carbonic acid, decomposing into water and carbon dioxide. So that's a very common one. Another one that's similar but different has sulfur, or SO3, instead of CO3. Now this does exactly the same thing. H2SO3 decomposes into water and SO2. So it's analogous to the carbon dioxide one. Very similar. We also have a third one, and this third one is where we have ammonium hydroxide decomposing into water and ammonia. So there's a pattern here. In each of these reactions, we have this H2 and then some ion here, where we decompose into water and then one of our common gases. Notice each of these gases, CO2, SO2, and ammonia, are all listed up here. So what do we need to make sure we're aware of? Well, we need to be aware of the common gases, and we also need to make sure we're aware of the reactions that involve decompositions to gases. That would be carbonic acid, sulfonic acid, and ammonium hydroxide. All right, so let's go to the next page where we have a few more examples to do. And then we're going to summarize all of what we know about not just double displacement, but all of the different types of reactions in one table that we can use to sort of review what we know. And then we'll be done with this. So let's go to the next page. Okay, so let's do these last two examples. You might want to pause the video and try them yourself and see how you do, or just follow along with me as I go through it right now. So the first thing I'm going to do is identify the cations for each of the reactants. So we have hydrogen and we have sodium. And I'm going to just put a square around each of those. And notice I'm keeping off that subscript 2 on the sodium sulfite. That's because I don't care about that subscript. I really just am interested in these cations because these are the cations. This is the part that's actually doing the exchanging. The subscripts aren't moving around. It's just those cations. So let's write out the formula for the products for each of these. So we're going to have sodium going to be with bromide. So we're going to have Na with Br. And I'll put a space there for the phase. And then the other product, we're going to have hydrogen with sulfite. So we will have H and we will have SO3. And I'll put a space there for the phase as well. So now what we're going to do is write out the charge balancing, so get the subscripts correct. So let's look at each of these and get the charges. So we have sodium, which is +1, and then we have bromide, which is -1. Okay. So we have a 1 positive charge and we have a 1 negative charge. And if we add these together, we see that as it stands, it's neutral. So we don't need to have any changes to the subscripts. We just need 1 sodium and 1 bromide. All right, let's go see if that's true on this hydrogen with sulfite. So we have hydrogen, which is +1, and then we have sulfite, which is 2 negative. So if we look at this, we see we have only 1 plus and we have 2 negative. Now, this is not going to equal 0. So we need to change something about this. All right? We need to change the number of cations. So how many cations do we actually need to make this work out? Well, if the cations are +1 each, that means we need 2 of them. This gives us the 2 positive charges that we need to add to the 2 negative charges that we have to give us a total of 0. So the formula needs to reflect that, right? We need to have 2 hydrogens in the formula. So we're going to put a subscript 2 there. Okay, so these are our symbols. Now, you might notice something on this. You might notice that formula, H2SO3, that's one of our, on the previous page, that's one of our compounds that decomposes into a gas. It decomposes into water and sulfur dioxide. So I'm actually going to draw a line through it. You can do this as well if you want. Put a line through it, and I'm going to write what it really becomes. It becomes H2O, which of course we know is a liquid, and it becomes also SO2, which we know is a gas. Okay, so that's actually what happens to that sulfonic acid. It decomposes into a gas. Okay, so let's look at, we've got some of the phases here. And we've got the subscripts figured out. All right, we did the subscripts in this step here, and we got the phases for water and sulfur dioxide. What about the phase for sodium bromide? Well, if you look on your solubilities table, you'll find that bromide salts, especially of sodium, are always aqueous. They're soluble. So we can put an AQ there. Now, the last thing we need to do is mass balance this. So we need to make sure everything adds up on both sides. So let's take a look at both sides and see. Well, for some reason, there's a 2 here. That must mean something important that was written here. So we have the 2, and that means we have 2 hydrogens here, and we also have 2 bromide here. So let's check the hydrogen first. There's 2. Well, we see there's a water molecule, and that gives us 2 hydrogens. And there's no other place where hydrogen appears, so it seems as though hydrogen is balanced. There's also a 2 that affects the bromide, right? So there are 2 bromides. Well, notice here in my sodium bromide that I only have 1 in the formula. And that is, the subscripts are correct there. So what that means is I need to put a 2 coefficient in front of the 2 sodium bromide. Sorry, in front of the sodium bromide, there needs to be a 2 there. So let's look and make sure that when we fix that bromide, making that balance, we also need to make sure that the sodium is fine on both sides because there's a 2 there. And if we look at the formula on the left that involving sodium, we see that there's a subscript 2 next to sodium because sulfite needs 2 sodiums for it to be balanced. So that's good. We're balanced on sodium. Let's take a look at sulfur and oxygen. There's 1 sulfur in this formula on the reactant side. There's 1 sulfur and sulfur dioxide on the right. So that's balanced. Now, let's take a look at oxygen. There are 3 in this formula for sulfite. And you'll notice that sulfur dioxide only has 2. However, there's another oxygen over here in water. So oxygen is also balanced. So we're good. That example is done. Now let's take a look at the last double displacement example here. You might want to pause the video and try this yourself if you're feeling comfortable with it. So what's the first step? Well, the first step is identifying the cations. Now it's pretty simple with potassium hydroxide. It's just potassium. But what about this ammonium chloride over here? That one's a little bit funny. Now the reason why it's funny is that we have a polyatomic ion first. And that's not usually the case with ionic compounds. The only polyatomic cation that we know of, actually, that is ammonium. The only one that we do in this class is ammonium. So this is one of the rare cases where we are including a bunch of nonmetals as a cation, and it also has a subscript. So it's a little bit confusing. So I'm going to put the square, well, it's not really a square, the strange shape there that I have circled around ammonium to designate that as our cation. Because that's the cation that's going to go over here where potassium is. Potassium is going to go over there where ammonium is. So let's write out all of our symbols. And again, it doesn't matter which one you start with first. I'll just kind of arbitrarily pick here to start with potassium. So I'm going to write potassium first, and potassium is going to be with chloride. Okay, a little space for the phase. And then the next product is going to have ammonium in it. So it's going to have that NH4. Right? The reason why we're carrying that subscript over is because ammonium is a polyatomic ion, and it needs to have that subscript to make it ammonium. If it didn't have that, it wouldn't be ammonium. So we've got ammonium hydroxide. Ammonium with hydroxide. So I'm going to write that there. And that's our anion with it. So let's put a little space for the phase. Now let's look at this. We've got potassium chloride and ammonium hydroxide. Let's make sure the subscripts are correct before we do anything else. So we do some charge balancing here. We've got potassium, which is +1, and we've got chloride, which is -1. So we only need one of each of those. We've got ammonium over here. Ammonium is +1, and hydroxide is -1. I just started writing an H there. Did it again. OH is -1. There we go. We have one of each, and that is a charge balance compound. So that's good. But you might notice, while this is aqueous, that ammonium hydroxide over here is one of our things that decomposes to a gas. So I'm going to cross this out, put a line through it, and replace it with what it actually turns into, which is NH3, which is a gas, and water, which is a liquid. That's one of our common gas decomposers. So it decomposes to a gas, which you will see that symbol DG when you're in the lab doing double displacement on the chart. When you see that on the chart, that's one of the things that decomposes to a gas, and you just need to make sure that you know which gas it decomposes to plus water. Okay, so we've got ammonia gas and water liquid and potassium chloride, which is aqueous. So we've got our symbols down, our phases, and now we just need to make sure everything is balanced. Okay, so we've got, let's just balance everything. We've got 1 nitrogen over here, 1 over here. We've got 4 hydrogen atoms over here, and there's another one here. So if we add all of those up, it looks like there's a total of 5 hydrogen atoms. Well, we've got 3 here, and we've got 2 here. So that's 5. Okay, now we look at chloride. There's 1 on the left, and there's 1 on the right. Potassium, there's 1 on the left, 1 on the right. And hydroxide, there's 1 oxygen in hydroxide, and there's 1 oxygen in water. Our hydrogen we already balanced because we said that there were 5 hydrogens total on the left, and there are 5 on the right, so we don't need to worry about these 2 or this one. We've already done that. So everything is balanced. We don't need to do any more changes to the coefficients, and that's pretty much it for double displacement reactions. So let's do this final section here. And this final section is a summary of all of the types of reactions that we've learned about. So when you're going and you're looking at, some random reaction that I put like on an exam, or you see it in the lab or something, you want to be able to sort of identify what it is. And we've learned about 5 types of reactions. And some of these reactions, like single displacement and double displacement, have some special things that we think about when we talk about them. I mean, they all have something special about them. And let's talk about what all of those are. So the first thing I want to do is go through for each of these reaction types. I want to talk about the format of the reaction, using the most generic symbols that I can, so that we can look at any kind of case and say, oh, that's a combination. It's not a combustion, or that looks like a double displacement, not a single displacement. So let's look at what those formats are. So a combination reaction, if you go back and you look at what we talked about, a combination reaction is literally we're combining 2 things. So we take A, and it could be anything really, A and B, and then those 2 things are our reactants. And on the product side, they're combined together. So we'll just call that C. Now, before we write any other notes about sort of special things about combination, let's look at decomposition first, and combustion also. So a decomposition reaction is actually the exact opposite of a combination. It's just exactly the opposite. So we have, instead of A and B turning into C, we have C turning into A and B. So instead of putting stuff together, we're making stuff fall apart or break apart. Okay, so that would be one of my notes for decomposition, is that decomposition is the opposite of combination. The other thing about decomposition that I like to highlight is that sometimes to make these things happen, we provide some sort of extra energy to sort of boost it along. And that can be in the form of heating. So sometimes we see heating on these. Not always, but sometimes. Okay, so decomposition is the opposite of combination, and combination is the opposite of decomposition. So let's write that up here in the notes for combination. It's the opposite of decomp. Okay. Now let's take a look at combustion. Combustion is a very, very specific and kind of special type of reaction. It involves taking something like element A or a compound A and doing a combination reaction specifically with oxygen. So you're combining something with oxygen. And the product of combustion reactions is pretty much always the same thing. We form oxides. So I'm going to write up here oxides. And the formula for an oxide is we have whatever thing we're making an oxide of, could be A, combined only with oxygen. Now, the ratio between A and oxygen largely depends on the identity of A. So we can have subscripts here, X and Y, that are going to basically depend on what A is, what type of metal, and so on. Okay, so let's write a few notes about this. One of the notes is that combustion reactions are combination reactions with oxygen. Another note is that products are oxides. Okay? And oxides will include things like carbon dioxide, water. Carbon dioxide is the oxide of carbon. Water is the oxide of hydrogen. You might also see things like magnesium oxide, right, where we have one oxygen with magnesium because magnesium has a +2 charge and oxygen has a 2 negative charge. So these are all examples of oxides. Okay? So that's what a combustion reaction is. It's combining something with oxygen to make oxides. Now let's move on to some of the special reactions that we learned about. Single displacement and double displacement. Now, single displacement is pretty straightforward as far as what we're usually seeing. We're usually seeing something like A, which is very frequently a solid, but not always. And we have another thing that I'll call BX. And what happens here is that A replaces B on BX. So we see A with X and then B on its own. That's a single displacement reaction. Frequently, we see this involving the formation, the change of a solid or the precipitation of a solid. So you'll see B turn into a solid where A was the solid before, but it doesn't have to be that way. Now, what's special about this, the notes about this, is that we use the activity series. And we use the activity series to predict when a reaction will happen or when it won't, based on the relative activity of A or B. So the reaction occurs when A is higher in activity than B. Otherwise, no reaction takes place. So if B is greater in activity than A, then no reaction. Okay, so that's the single displacement reaction. Now let's go on to the last one, which is double displacement. Now, we just did double displacement, so it's fresh in our minds. Let's just kind of write down what we have. We see that in a double displacement, unlike a single displacement, we have two different salt solutions. We have AX, and then we have BY. And these are our salt solutions. So usually these are aqueous. Now, in the double displacement reaction, what happens is both cations switch places with the anions. So we have A and we have B, and these exchange. Okay, and that's what a double displacement is. So let's write out the hypothetical products for this example. Okay, we would have A, in this case, being with Y, and I'll put a little phase thing there and I'll leave it empty. And then we're going to have B with X, and I'll leave that empty. And the phases of these will depend on things like the solubility. So I'm going to make a little note here that inside of the parentheses depends on things like the solubility, common gases, or if we do an acid-base reaction. So if we form a liquid, an acid-base reaction. Sorry, that's a little A/B, so let me write that out actually. When I write acids and bases, I usually write A/B, which means acid/base. Sorry about that. Okay, so that phase is going to depend on the solubility chart, common gases that we went over, and then if we have a molecular compound, that's an acid-base product, so a liquid. So another note to mention on this is that the reaction occurs when a solid, a liquid, a gas, or a molecular compound forms. Okay, so that's when one of these reactions happens. We have to have a solid, a liquid, a gas, or a molecular compound on the product side. And that's what I was saying those are driving forces that make the reaction actually progress towards the product side. So those are the 5 different types of reactions that we've gone through. We've learned a lot in this chapter. It's a large amount of information. And for that reason, in order for you to assimilate it, to be able to not get completely confused about all of this, you need to go through a lot of different practice problems to try all of these. And that's why I have the problem sets available on Canvas. What you want to do is go into those problem sets and keep this table handy and look at each of the reaction types and make sure you can identify and see whether it's a combination or a combustion or a double displacement or a single displacement. And then in each case, work through those different processes that I've shown you so far. So we go through writing out the symbols, we get the subscripts right, and then we do the phases, and then we balance it. Make sure you can do all those steps on a lot of different examples. That's going to really help you out, especially when you get to the test that we have coming up here pretty soon. So with that, I will end this lesson. I hope that it was helpful. Please let me know if you have any questions, and I will see you soon. Take care.